I'm going to show you how you would use the central limit theorem and create a simulation to answer specific questions. So imagine that you have a large freight elevator, and that elevator can transport a maximum of 9,800 pounds any given trip. The load that you're trying to carry contains 49 boxes. From experience, the weight of your boxes follows a distribution with mean 205 and standard deviation 15 pounds. So what's the probability that all 49 boxes can be safely loaded into the elevator and carried to whatever floor they need to be carried to? The first thing I should say, let's assume that every single box that we had weighed exactly the 205 pounds the average is. So if we multiply the 49 boxes by 205 pounds, we get, well, 10,045 pounds, which is more than 9,800 that the elevator can carry. Now, there's a standard deviation, and it's not always going to be the case that every box weighs 205 pounds. I mean, there might be some boxes that weigh less than 205 pounds. There might be boxes that weigh more, obviously, but the question is, what's the probability that we would get enough boxes weighing less so that we would be fairly certain that we can load them onto the elevator? Now we'll simulate a few scenarios. I didn't say anything about the type of distribution. I didn't say it was normal, for instance. For now, we're going to assume that they are normally distributed, and we'll see what happens. So I'm going to start by setting a seed, and the seed is there to ensure replicability, so that if you try the same exercise on your computer, you'll get the same results that I do here. So we set a seed at 0, and we're going to generate 49 weights from a normal population with mean 205 and standard deviation 50. So here are my 49 weights. You see, some of them are above 205, some of them are below 205. Let's plot a histogram with 10 bins for the data that we have. This is where they are. See, there's a fair number of them that fall below 200 pounds. Now, since the elevator can transport up to 9,800 pounds, well, 49 boxes will be able to be carried on the elevator. If their total weight, 49 times the sample mean, is less than 9,800 pounds. We know how to compute the sample mean. We just use the mean function. So 49 boxes times the mean of the 49 boxes should give us a total weight. And in this instance, it's like not as nice as we would want. It's definitely not below 9,800. So that one won't work. But what if we use a different one? I'm going to use a different seed, again, just so that you have the same result that I do. And I'm going to compute the sum of the weights of 49 boxes that I'm randomly selecting from a normal distribution with mean 205 and standard deviation 15. That computation here is equivalent to doing 49 times the mean. What do we get for this one? Oh, we're getting close, but still it's too heavy. 52 pounds too heavy. Except we've just done 2 tries here. We can't establish a trend with 2 tries. We can't estimate the probability that the sum of the weights would be below 9,800. So instead we write a little function, and what the function will do, it will help us find an estimate. It's a super simple idea. If you try a large number of random combinations of 49 boxes, the proportion of attempts for which the total weight is below 9,800 is going to be an estimate of the probability that the sum would be below 9,800. Here is the code that will do so. It's a function that takes into account the sample size n, the threshold for the total that we need to be below, the mean value of your normal distribution, the standard deviation of the normal distribution for the weights of the boxes, and how many simulations you're willing to run. So if I combine all of this here, well, I see nothing. All I've done is I've compiled the function. What's really happening is it's keeping track of all of the times where the total is smaller than the threshold. And at the end of the routine, it's going to estimate the probability by looking at the number of successes, how often you were below the threshold, divided by the number of simulations that you've run. We'll try the experiment 10 times, 100 times, 1,000 times 10,000 times, 100,000 times, and 1,000,000 times to see what kind of probability we get. So here's a 10 times, 100, 1,000, 10,000, 100,000, and 1,000,000 times. If you just run it 10 times, you had no success. If you run it 100 times, you had one success. 1,000 times, about 0.7% of the cases were successes. 10,000 times, it looks as though you would expect there to be success about 1% of the time. That's a low percentage of success. That's a low probability that your 49 boxes will be below 9,800 pounds. Perhaps it's because we used a normal distribution instead of some other distribution. Like we could have used a uniform distribution, you name it. So I'm going to try it here with other types of distributions. Let me just show you some code here for the uniform distribution. So we need to come up with a new piece of code that would do the same thing, but instead of calling a normal distribution here, it's going to have to run a function where it calls the uniform distribution so that your minimum and maximum values will not be the same thing as the mean and the standard deviation. This function requires different parameters. And I've picked these parameters so that they would have a mean of 205 and a standard deviation of 15, which is why we're seeing 179.02 to 231, roughly speaking. It's a uniform distribution where the mean is 205 and where the standard deviation is 15. So I'll do it with 10, 100,000, 10,000, 100,000, and 1,000,000 cases. I get sensibly the same results here. About 1% of the time, independently of whether I use a normal distribution or a uniform distribution. It's not too surprising because all of these results are part of the central limit theorem. What we're interested in estimating is the probability that the sum is smaller than 9,800, and there's 49 boxes. So what I really want is that the mean weight for boxes in my sample should be below 9,800 divided by 49, which is exactly 200. Now, according to the central limit theorem, the distribution of that mean is approximately normal. It's exactly normal if the underlying population is normal, but if the underlying population is not normal, then it's approximately normal. The mean of that distribution would still be 205, but the variance would be 15 squared, 15 being the standard deviation of the underlying distribution, squared to get the variance, divided by the number of observations. And here we have 49 observations. So how do we compute the probability that the sample mean will be less than 200? Well, we know n is pretty big here. And if the mean of the underlying distribution is 205, 15 squared divided by 49 actually gives us a small variance. It's unlikely that the mean will be below 200. But we can compute it, right? We just standardize. We want the sample mean to be below 200. So we take this 200 threshold, we subtract the population mean, which is mu 205, and we divide by the square root of the variance of the sample mean. So the square root of 15 squared divided by 49. And so what we need is a z-score of minus 2.33. So you're looking for the probability that if you were to draw numbers from the standard normal distribution, they would actually be smaller than minus 2.33. It's more than 2 standard deviations away from the mean in the negative direction. You wouldn't expect that to be super high as a number. How do you compute that in R? You use the p-norm function. That's going to compute the cumulative value of the normal distribution from minus infinity to this threshold minus 2.33 that we have here. And we need to do this with the standard normal, with a mean of 0 and standard deviation of 1. And we get, roughly speaking, this 1% that we had seen before. So it's highly unlikely that you can carry all boxes together. Now you might be interested in asking questions such as, well, what would be the threshold required to reach a probability of success of 10%, 50%, 75%, given that the underlying population has a mean of 205 and a standard deviation of 15? I'm going to show you a bit of code that does it. Here you're looking for the threshold required for this cumulative probability to be below 10%. And these quantities here are the various thresholds that you could try. Like currently we have 9800, but obviously we'll need to modify the threshold a little bit to find the threshold that gives us probability of success to be 10% or smaller. I'll want to find the largest threshold, which gives me this probability of success. That's 99.10. So if my threshold for the elevator moved from 9800 to 9910, it's an extra 30 pounds, then 10% of the time I'd be able to load it. And if you want to know what the weight would have to be for you to be able to load it 50% of the time, you just modify this 0.1 by 0.5. So if the threshold was at 10,044, then you'd be able to load it 50% of the time. Do you recognize that number? That's roughly the product of 49 times the mean value for the weight of the boxes. That's not surprising. This is what you would expect to see. And if you wanted to know for 75% the loadings being successful, you replace 5 by 75. You'd need your threshold to be 10,115 pounds.